Good day, good evening to all of you. What a great turnout for today's webinar. Thank you all for finding time in your busy schedules to meet with us. My name's Ward Patton and I'm a Valmet partner hosting today's webinar. Before we begin, there are a few housekeeping tips to go over. First, all attendee microphones are muted, but if you look at your GoToWebinar toolbar, probably in the upper right corner of your screen, there is a questions feature that will allow you to type and submit questions to the presenter, which we'll then answer during the Q&A session at the end of the webinar. Next, if you have any issues with audio, video, or connectivity during the webinar, call the GoToWebinar technical support at 833-851-8340. Their staff are standing by to assist you with any technical difficulties. They do recommend that you use Chrome or Firefox as your browser during this webinar. Finally, we're recording today's webinar and we'll be posting it on Valmet's YouTube channel within a day or two. Now, let's begin today's webinar. Alfredo Sarli, your presenter today, has over 25 years of experience in the paper industry, working in various functions ranging from the wet to the dry end of the paper machine. He's currently an application specialist in Valmet's Air Systems division and is based out of Montreal, Canada. Today he will be discussing drying optimization and how the Valmet XT Control system can be used to reduce your energy consumption. Over to you, Alfredo.
Thanks very much, Ward. I appreciate it. And thank you to everyone who joined us online today for this webinar. And I want to get started right away with the topics I'd like to review. I want to begin with the theory on hood drying and give some background on that, and also discuss the hood design parameters that affect drying optimization. I'll have some case studies throughout that I'll be presenting, and once we square that away, we'll get right into the XT Control system, its principle of operation, and the various components that form this system. And at the end, I'll have a final case study and some references of where this system is being used. And before we end today, I'd like to provide some recommendations on setting up an energy optimization program at your mill. And of course, as Ward mentioned, at the very end, we'll have questions and answers. So, drying is the most energy-intensive process in paper making. In this chart, we can see all the various components of that require thermal energy. The distribution is very heavy towards the green portion of the pie, which is represents the pre-dryer hood cylinders. Next, biggest part of the pie in black is the hood supply air, and so on. The subsequent components get smaller and smaller. If we just wrap up, or if we just look at only the contribution from the drying, then that represents over 80% of the thermal energy consumption. So today, then, we'll be looking at the dry end of the machine, the hood, or the closed hood, as we see on this image, and the associated air system with this hood, sometimes called the process air system. In Europe, it can be called the hood ventilation system. That's composed of the equipment you see behind the machine on the drive side, up on the mezzanine there, a series of fans, ductwork, and as well as heat recovery components that we see. And so this air system extracts the air from the hood and drives it out through the stack to atmosphere. Let's review some metrics so that we're on the same page with regards to discussing energy consumption. What is typically done is a tracking value of tons of steam per tons of production is used. But unfortunately, we feel that doesn't correctly represent the true rate or the actual efficiency of the drying process. And I'd like to demonstrate. I want to illustrate it with these two cases here. We have two paper machines on the left and on the right that are identical, making the same grade at the same production of 48 tons an hour. The machine on the left consumes 48 tons per hour of steam, so that's the green arrow just below the hood. And it uses that steam to evaporate 38 tons of water that came from the sheet as it dried, and it accumulated into the hood and is to be exhausted out to atmosphere, the light green arrow above the hood. On the right-hand side, we have the same machine, same production, but it happens to use 57 tons of steam. So considerably more. If we do the ratio for 57 over 48, we get 1.2 tons of steam per ton of production. But the machine on the left, if we do 48 over 48, we get 1 ton of steam per ton of production. So the conclusion seems to be that the machine on the right is consuming 20% more steam to do the same job. But that's not the case. If we need to also look at the inlet conditions. The machine on the left, after the press section, the sheet's coming in 52% dryness. The machine on the right, on the other hand, the sheet's coming in a little wetter at a lower dryness of 48%. So those 4 percentage points represent more water for the hood to evaporate. So in the upper arrow, the light green arrow, the evaporation load of the hood, we see 46 tons of water to evaporate. That's almost 20% more than the machine on the left, which had 38 tons of water to evaporate. So if we want to truly compare the two machines, we need a different metric. We know that the machine on the right is doing more work than the machine on the left. It has a larger evaporation load of 46 tons instead of 38 tons of water to evaporate to atmosphere. If we do that ratio now of the metric that we're proposing, tons of steam used per ton of water evaporated, then what we get is 1.25 for both machines. In fact, we take the 57 on the right divided by 46 evaporation load, we get 1.25. Same thing on the left, the 48 tons of steam used to evaporate 38 tons of water, 1.25 as well. So we believe this is the correct metric because it takes into consideration the inlet conditions, and that being the sheet dryness. So before we embark on any energy efficiency or optimization program, we recommend that we make sure that everything leading up to the entrance to the hood is taken care of and is maximized, or I should say optimized, to have the optimum sheet dryness entering the hood. If we optimize that, then we can ensure a better success with our energy optimization program. Just to review some theory then, there's two ratios that I'll be talking about today. The first one is the hood humidity rating. This is the rating that each hood has in terms of its ability to do work, the amount of work and the quality of work you can do. In green, I have on the top left-hand side the ratio, which is expressed as the total evaporation load that we saw earlier, the top arrow in the diagram before, one slide before, divided by the exhaust air required to move that amount of water out of the hood. This is a dimensionless ratio, so the units on top and bottom have to be the same. So we use pounds of water for the evaporation load in the numerator and pounds of dry air being used by the hood in the denominator. Since it's a dimensionless ratio, it can be easily replaced to convert it to a metric format. So we could have kilograms of water in the numerator and kilograms of air in the denominator. Okay, let's illustrate that with an example. Here, this hood uses 200,000 pounds of dry air every hour in order to exhaust the evaporation load of 26,000 pounds of water coming off the sheet. So if we punch that into our ratio, we get the 26,000 pounds of water on top divided by the 200,000 pounds of dry air in the denominator. 26 divided by 200 gives us 0.130 pounds of water vapor per pound of dry air. Since, as I mentioned, it's a dimensionless ratio, it can easily be 0.130 kilograms of water per kilogram of air. Now, I know that in Europe, to avoid having to always mention the decimal point, we can just convert that to grams, as that's the range it's usually in. So that 0.130 becomes 130 grams of water per kilogram of dry air. Likewise, in North America, in common usage and everyday usage, don't like to avoid having to use the decimal point. There's a conversion that was done over so many years ago, a very interesting one, an odd one to be sure. It's grains. For those who are familiar with this, there are apparently 7,000 grains for every pound of water. So if we multiply that 0.13 by 7,000, we get 900 grains. So that's the common usage, and 900 grain loading is pretty much the standard throughout. The great number of machines running in North America are in and around 900 grain loading. Some of the more recent offerings tend to push that ratio up, and that performance is pushed up from 0.13 up to 0.16 pounds of water per pound of dry air. Multiply that by 7,000, and we're talking about 1120 grain loading. And I indicate in that green box that this leads to high or higher energy efficiency for these high humidity hoods or higher humidity hoods. And why is that? Well, if the ratio is higher, then the number is higher at 0.16 compared to 0.13. It means that either the numerator is bigger or the denominator is smaller to get that larger number. So practically, that means either in the numerator, we can evaporate more water for the same amount of air being used by the hood in the process air system, or conversely, if we are looking at the same grade with the same amount of evaporation water, we can accomplish that job with a smaller denominator, meaning a smaller amount of dry air being used. So the air system is processing less air, which means less air to heat and less air to push through the system. So that being the electrical power. So there would be less steam being used, less thermal energy, in other words, and less electrical energy. So let's look at what dictates how a hood is rated and why one hood would have a higher rating than another. Let's look at the thermal energy of a hood. Here in this thermal image, the scale ranges from 20 degrees C, ambient room temperature, let's say 70 F, all the way up to 60 degrees C. So the indicator bar on the right shows the variation. The dark blue is at the bottom, 20 C, and at the very top, in very bright yellow, almost white, is the 60 degrees C. So in this image, most of the hood is in dark blue, as it should be, because it should keep the heat energy inside the hood and not transfer through or out of the hood. But there are weak links throughout the system, as is unavoidable, because there are points where the heat can escape. For example, you can see around the framing of the felt access doors, which have a brighter red, almost yellow circling around them. Likewise, along the top of the front lifting panels, between the top of those panels and the fixed top portion of the hood, and also along the floor level where the doors come down. If some air leaks out, well, that's what we're seeing with that red. I'll also draw your attention to the panels themselves. in between the vertical panels, you'll see there's a slight bright lighter blue line. What that represents is where the panels connect. So where the connection points are of course, it's not a full panel. This is to enable installation and fabrication and so on, bringing these panels together. That's going to be the weak link in the chain. Those areas are also insulated, but of course, since it's not solid panel, some heat energy will go through, but you can appreciate that it's very little compared to the bright yellow or reds. It's just a very light blue, but that's what those lines indicate. So in summary then, the four factors that affect how high a rating, an exhaust humidity rating a hood can have, is based on the four mechanical factors that we mentioned. First of all, the physical condition of the hood. Is it in good operating condition? Is it a very old hood with a lot of damage that needs repair? Or is it a fairly new hood? Or it's a hood that has been maintained very well? The physical condition is the first thing to look at. Secondly, the insulation quality and the coverage, as we discussed with the hood panels. Thirdly, we mentioned the through metal between the panels that we see in light blue. They're the ones that create thermal bridges between the inside of the hood and the outside ambient air. Those thermal bridges have to be minimized in the quality and construction of the hood so that we can minimize air escaping out, or vice versa, having cold air condensing from the outside, condensing the hot air on the inside, allowing the evaporated water to recondense and then start dripping. And lastly, all of these really just sum up to one notion, which is how well sealed is the hood? How good is it at keeping the hot air in? How tight are all the seals? And how did we work to minimize any possibility for leakage air to enter the hood? Let's talk about that leakage air and what impact it has. On the right, we see the hood with the leakage air coming in at room conditions, ambient conditions. That air that enters the hood, that leaks in, it has no choice but to be heated up by the drying cylinders. It will enter the hood, therefore it will absorb that energy, and so it will be heated up. So that's where there's a loss of energy. And that air gets exhausted out to atmosphere, and so that's where we encounter a loss. We tried to quantify this in the graph. We see the quantity of leakage air on the x-axis, 10, 20, 30, 40, up to 50 kilograms of dry air per second. The green curve is the energy being lost, and if we apply the energy cost, then on an annual basis of the area that we're dealing with, in this case in Europe with the euros here, 50 kilos of dry air per second can represent well over 400,000 euros per year. So a very significant amount of money, almost $500,000, $500,000 per year. So we want to minimize this leakage air. We also spoke of the electrical energy savings. And interesting to note that a very small change in airflow can mean a big change in required fan power. From the fan laws, we know that airflow is in direct proportion with rotational speed. So in the graph on the right, we have the airflow quantity going 0 to 100. You can think of that also as the rotation speed, 0 to 100%. And on the y-axis, the fan power in percentage. Why do we have this kind of very steep curve? Well, from the fan laws, we also know that in the rotational speed is related to fan power to the third power. In brackets, we see N2 over N1. So if we change, let's say N1 was the operating condition at 100%, and we bring it back 10% down to 90%. So N2 now is operating at 90. The 90 over 100 is 0.9. To the third power is 0.728. So that means 72.8%. It would be dropping the airflow by 10% would drop the electrical consumption down by 27%. So there's a strong impact there as well. So we've reviewed the thermal energy, we've covered the electrical energy. Let's look at a case example. Here's a hood that is running at 100% fully open. So this is a case study that we did. All the controls, all the hood exhaust controls were 100% open. The evaporated water was exhausted from the dryer section with an average air humidity of 109 grams of water per kilogram of dry air. Recall from that ratio before, that can also mean, it can easily be converted to 0.109 pounds of water per pound of dry air. But the hood, though, on the other hand, was dimensioned for 160 grams of water per kilogram of dry air. That's like saying 0.16 pounds of water per pound of air. Or in grains, it was exactly the example before for the high humidity hood of 1120 grains. So the hood is underperforming. It's not operating at its maximum or at its optimum rating. It's processing air out at a significantly less amount than it is capable of. As a result, it creates the problem of leakage air. There's 57 kilos of dry air per second that is leaking in. And this air is going to be heated by the cylinders either way. And so what does that represent in terms of cost? It represents about 2.8 megawatts of energy of increased steam consumption, which is about almost 5 tons of steam per hour, which represents about 7% of drying section steam consumption. So it's important that we just want to illustrate that it's important to optimize this, and that's what we are proposing to do. Okay, so let's summarize the operating conditions for the hood. We want it for it to be designed for consistent long-term operation at high humidity. Such a hood design would include full width and full length false ceiling with adjustable doors or adjustable dampers to adjust the pressure within the hood and the distribution. We want there to be minimal leakage. We want a good, well-functioning exhaust air humidity and air balance control system. And an extra benefit is if the hood can be pre-assembled at installation by bringing in large modules instead of bringing in panel by panel. So in the case of the bullet item on the well-functioning exhaust air humidity and air balance control, those two ratios that we just saw, you can see there's a lot of calculation there. And if it changes there's a lot of parameters to consider and components to optimize. And then if the grade changes on a regular basis, then all that has to be redone. It becomes a little bit more difficult to do in a manual way. And so what is being recommended is to automate that process. And that's where the XT Control system comes in. The XT Control system takes note of all these factors that we've just discussed and automates that process. So if you can see my cursor here, then let's start with the hood exhaust, which is the red duct. The hood is exhausted out through the exhaust fan, and before it goes out to atmosphere, it is recommended to use heat recovery because all this optimization that we are doing can be brought to benefit if we can monetize the savings in heat recovery, recuperating that heat that we've put in and bringing it back into the hood. To do so, then, we put it through a heat exchanger that will take ambient air, preheat that air, bring it up to the condition that we need to supply the hood. Usually, the heat exchanger alone is not enough to bring it up to set point temperature, so we need some steam coils to bring it up to set point temperature, and then the supply fan pumps that back into the hood. The control system takes all these various measurements here. For example, we can take air humidity measurements on the exhaust. to see where we are on the exhaust, send that in to an exhaust airflow control according to humidity, so that that signal is translated to the speed control on the fan to adjust the exhaust flow. While at the same time of measuring the humidity, we also want to measure the flow going through there, so we can double check that, and that's where we would have this airflow measurement right here. This airflow measurement, along with the airflow measurement on the supply air, is fed to the supply air control so that it can adjust both the speed control on the supply fan to make sure we have the right amount of air going through, and it can be used for the zero level measurement. And this zero level measurement is a series of measuring ports that tell us where the zero line currently is and how we can move it to adjust it accordingly. The control parameters that we use are the hood exhaust air humidity set point, which can vary according to hood exhaust air temperature. So we program in the function that is required to get the optimum humidity, and therefore the control strategy is that we want the set point of the exhaust air humidity to be calculated based off of the exhaust air temperature. We want this humidity to be measured and controlled via the exhaust fan speed. We want the supply air flow to bring the air balance into the correct ratio that we discussed before, the 65% that we mentioned. We want the zero level measurement to be done and to be used for fine tuning the air balance and to situate it, that in that range just above or below the top of the front access door, which is about 1 to 2 meters. And in this process, we can also control the supply air temperature, which is controlled by this fresh steam coil here to have the optimum supply temperature provided. The components that accomplish this, for example, let's look at the zero level measurement. Here we see a series of 5 measuring ports. The principle, very basically, is that you remember from the graph, the top part of the hood is under positive pressure, the bottom part is under negative. If it's under positive pressure, it'll blow air out. So what the sensor sees as the air is coming through is it'll predominantly read the higher internal temperature of the hood, and so it'll signal back it's under positive pressure at this point. As we go down, the pressure will reduce, and so therefore the temperature going through that will be read will follow suit. As we head down towards the bottom part of the hood, it'll be under negative pressure, so there's the tendency will be for the ambient air to infiltrate into the hood. And so now, as that air is coming in this direction instead, the temperature sensors detect a markedly lower temperature. Since the ambient air is significantly lower, it'll see these conditions here of, let's say, 30 degrees Celsius. So depending on which ones are under positive, which ones are under negative, allows us to establish where the zero line currently is so that we can optimize it and bring it up to the required level. For the flow measurements, we use flow bars. This is the same principle as the pitot tube measurement. The two measurements here in the direction of the airflow. So these are inserted into the air ducts, either the exhaust air duct or the supply air duct. So much like the pitot principle, we measure the total pressure, subtract off the static pressure and perpendicular to that flow, and the difference giving us the velocity pressure, which we can translate into flow. For humidity sensing, we make use of various humidity sensors available on the market. Of course, they're inserted into the duct, and here we see in Europe, the Vaisala brand is more common. In North America, we see more of the MAC units for humidity measurement. So let's summarize the factors affecting energy efficiency in the dryer section. We talked about hood exhaust humidity, that ratio being as high as possible for the hood to, as long as the hood can handle it. We want to minimize the leakage air into the hood and have an optimum air balance ratio. That was the second ratio we talked about. We want to make sure that the construction of the hood is adequate and in good condition, meaning the tightness and the sealing of the hood. If we want to take benefit of this optimized air, then we need heat recovery. So we need to make sure that the heat recovery is functioning, or that there's adequate heat recovery. We want to make sure that the supply air temperature is in the right range. There's sometimes tendency to have supply air going to runnability components where the temperature is too high, and that's wasted energy at that point. So the control system helps manage that, which is a lot easier to do than to do it manually. And finally, this is a given because the pocket ventilation is now on almost every machine, if not all machines, and that is an important factor because that affects that affects the efficiency right at the source, of course, right in the dryer pocket. So with all these conditions in place, we can expect to have an improvement by increasing the exhaust air humidity ratio. If we move from the 0.12 up to 0.14 or 0.16 humidity, then what the benefits that we can see are the following. Let's take the case of a hood that is set at a supply air ratio of 65%, and the hood is capable of operating at 0.16, which is the 1120 grains. Well, then in that case, we could see an energy consumption of just below 3,000 kilojoules per kilogram of water being evaporated. A number of these systems have been put into operation. If we look at the last 10 years, Valmet has had 50 hood deliveries, 45 of which have complete control systems on them. In 2018 alone, there were 8 startups of hoods, all with control systems. These systems are also available on rebuilds as well. So it is possible to do so on an existing hood. One case is in China, where the benefits that were seen in this case study was that, well, the project, first of all, was a full scope blow box upgrade, and also optimization of the dryer section ventilation. The main benefit was that hood air balance was improved, which means that the 2 ratios were improved. The first one being the air balance ratio, so spill was reduced. And the second one, the exhaust air humidity was optimized, and so the exhaust volume was reduced. So less exhaust air to be processed, and they're meaning less supply air to be made back up and brought up to temperature, and thermal energy being spent on the steam to bring that temperature up, and electrical power on the fans. In all, the energy savings were about 500 kilowatts, which represented 5% savings for them. And so the ROI on that system was about 4 months. This is an example of the control screen. I want to highlight some of the reporting that the system does. Here we see that the ratio for the exhaust humidity, the grams of water per kilogram of air, being optimized here in these exhaust stacks, up to 0.14 pound per pound in one case, and up to 0.16 being the maximum for that hood in the hood exhaust air stack number 3. For this particular machine, the ideal ratio, air balance ratio, was 60 about 60%. And so bringing all these factors into consideration, that was the optimum ratio for the optimum amount of energy efficiency that they could achieve. So before I finish off today, just want to give an idea of an improvement plan that can be put into place. There's a lot of things that I've discussed, and there's a lot of factors and a lot of parameters to look at. The control system, of course, helps with all this, but a stepwise plan would be a wise way to approach it, because because of the fact that there are so many steps involved. So the opening slides, we saw that we compared two machines that were running at about 1.25 tons of steam per ton of water to be evaporated. Well, this particular machine in this case study was up as high as 1.6. The idea was to bring it down, and we believe that the ideal, the optimum point that we can bring it to feasibly is about 1.1. And in this case study, there was a 25% reduction, but it was done in steps. The first step was to look at what, the baseline, what the machine was doing. Secondly, was to optimize the hood ventilation. So, bringing in that control system enabled the improvement on the two ratios, the air balance and the exhaust air humidity. That brought an improvement where the steam consumption went down from 1.6 to about 1.5 tons per ton of water evaporated. There was a rebuild on the existing air heat recovery. There were some losses there in the system. That was brought up to spec and replaced with new heating elements. And so that brought another reduction to about almost 1.4. And the biggest step, of course, was now that we had better energy quality available from the hood, having done all these, now we can make use of it for more heat recovery. So there was an opportunity to make use of processed water heating. And so that brought a big impact, but to almost reaching the goal of 1.1, it was just below 1.2. But this would not have been possible if all these other steps were not taken on this new sprint machine. So to summarize then, we recommend that first of all, we need to know where we are. We need to do a baseline, and that can be done either very quickly with a quick scan type of audit, or a more thorough study would require like a more thorough energy analysis, can be done over the course of a couple of days at mill site. But the must-do issues first before attempting or to change anything on the system is to make sure everything leading up to the hood is optimized. Do we have the highest sheet dryness after press leading into the hood? We saw in the opening example that played an important role. We need to look at the hood itself and make sure that we're working with a hood that is in good condition. After many years, it's normal that there's some repairs or corrections that need to be made. So that needs to be done before we take on such an optimization program. And then once we've done that, then we start optimizing the energy efficiency as related to the air balance and the exhaust air humidity. And once we've done that, then we're in a position to be able to monetize this benefit and to convert it into savings. So we have to make sure that we have the proper heat recovery, or that we have enough heat recovery, including water heating, which provides a very big benefit. And once we've done that, it's important to maintain these savings over time. And the way to do that is to follow and to monitor. First of all, we need to follow the correct parameter, and we recommend the tons of steam per ton of water evaporated and not per ton of paper produced. And secondly, to help us, we recommend an automatic air balance control system because doing it manually can be very complex, especially if there's many grade changes and so on. So that's where the XT Control system helps out significantly. Because if the benefit is not, if the process is not measured, as we know, then it cannot be controllable. And on that, it ends my presentation for today.
Excellent presentation, Alfredo. Thanks. Before we get into the Q&A portion of this webinar, let me say that we've already had a question about this. Alfredo's presentation is available in PDF form. Just email him at alfredo.sarli@valmet.com and he'll be happy to send you a copy. We received a number of questions already, but you can still submit them during this Q&A period right now. If Alfredo can't answer them today because he needs more information or the question deals with confidential matters, he'll be sure to email you with a comprehensive answer after the webinar. Alfredo, go ahead and take it away for Q&A.
All right, thank you, Ward. All right, the first question is, what types of machines are ideal for the XT Control, what grades and basis weight ranges? Well, the system is offered with all new paper machines and that are delivered by Valmet, and it covers of all grade types and basis weight ranges. There's only very few exceptions, that being maybe in the case of very low grammages, and that's because very light specialty grades have a very low evaporation rate. Or the other exception is in the case of single grade machines where the setup can be done manually, and therefore if it doesn't have to change, then it's easier to set it up and let it run long term. And so a continuous control system would not be necessary in that case, or if there's little to no heat recovery to monetize that savings. But that's a small minority. So in the great majority of cases, the system is applicable and is beneficial. Let's see. Another question here. Since higher efficiency hoods remove more water per unit of air, is it feasible to upgrade an old hood without having to make changes to the support system equipment, fans, auxiliaries? Yes, good question. If the hood is able to remove more, that's the first step in it. But of course, the air system is also integral. So it depends. The answer to that question is it depends on what the capacity of the existing air system is. If it has that capacity, the hood has a higher capacity and a higher performance. Will the air system follow? So that's a case-by-case situation. In some cases, it would mean reducing the amount of exhaust air and supply air. So in those cases, yes, of course, the existing air system can handle it because it will require less volume. But we would recommend that during the course of an audit to verify that, so that we can make sure that the air system is adequate. Okay, another question. Since hood efficiency is related to heat loss and leaks, are there certain sections of the hood that could be upgraded to get a significant bang for the buck and not need to replace the entire hood? Which sections of the hood tend to lose the most heat and or have the least insulation, and therefore enough savings benefit to replace only those? Well, that's definitely the starting point. And the answer is yes, we need to address the state or the condition of the hood first before we embark on anything further. So in the last case example that I showed, we did get a benefit out of improving the condition of the hood by sealing the hood better. Then we can increase the hood exhaust ratio that it is capable of doing, and therefore get a benefit right there. As to which sections would benefit the most, I would say closer to the wet end, of course, where there's harsher conditions, more water vapor present might lead to faster deterioration of the hood. So those would be the first places we would inspect in an audit. That was a very good question. Okay, another question here. What basis weight would you avoid? Yes, of course. I would say the very low basis weights, specialty grades that have very little evaporation, very low evaporation rates, so very difficult to work with that. Another question here: how do you differentiate between changes in press solids versus drying efficiency? Oh, very good question. I have seen in multiple studies that 1 percentage point of press solids can yield up to, and I say up to, 4% in productivity increase. So yes, there's a strong correlation, and it can be as much as 4 percentage points. Some have claimed higher. I've not seen it, like 5, but of course there's also the probability that it could be. Let's say a range would be between. I would give a range between 2 and 4 for every percentage point of reduced of improvement in dryness at the inlet. Okay, I think we're almost running out of time, so I'll take one more. I'll just read one more question, and then any other questions that I've not addressed here, I will be happy to respond to you afterwards by email. And also, please, if you have the opportunity to connect, also by LinkedIn, that could be another easy way we can communicate. I'll be very happy to hear from you. Okay, last one here. You have focused on energy consumption. I've seen some good information on how your operations affect overall costs. Can you comment on optimizing hood operations for maximum paper production? Is there an upper temperature of PV where the increased temperature does not contribute greatly to increased drying rate? Interesting question. I guess I would like to discuss this one further with you because our belief is that, above 180 degrees Fahrenheit, there's not much benefit that you can get from, pumping that into a PV. So that's pretty much wasted energy above that point. I've seen numerous machines running at 200 degrees Fahrenheit, and it's just a sledgehammer effect over years of trying to correct problems and issues and so on, and trying to increase it. But it does not provide, unfortunately, a benefit. So this would be a case by case, and I would love to address this one. This is an interesting one. So if you could, I'll follow up with you by email on this one, so we can discuss it further. All right. Well, I think, Ward, maybe it might be best to stop at this point, and I'll get back to the others by email.
That sounds good. Thanks for all of the questions that we've received. I hope we were able to respond to most, if not all of them. Again, if not, Alfredo will follow up via email with anybody whose question we were unable to answer or had a question that really needs more of an answer than we were able to give today. We'll also be emailing you a link to the recorded webinar as soon as it's available on YouTube. If you have any further questions, email alfredo.sarli@valmet.com. or reach out to him at LinkedIn. He can go more in depth with you about any air system needs you have. We hope you gained some valuable drying optimization and energy consumption knowledge today that can help you move your mill forward. Thank you all for giving us your time today, and we hope you'll join us at future Valmet webinars. Bye-bye.